Welcome to micro communication course. Today we will learn AS parameters or a scattering matrix or a scatter parameter. Now you know that the parameters you have learned earlier, that is about a Z parameter, Y parameter, then hybrid parameter, then ABCD parameter. All the parameters you have learned earlier, and all these parameters are used at a low frequency. These are the parameters that can be used to model a circuit at a low frequency. That you should know. But since that your microwave circuit, that frequency is high, to model the microwave circuit at a high frequency, this Z parameter, Y parameter, H parameter, or ABCD parameter will not be used. So that's why that scattering parameters have developed or designed to model the microwave circuit or to analyze the microwave circuit. These are the S parameters that are used at a high frequency, and all these parameters are work at a low frequency. This S parameter is called as a scattering parameter. Now, why this Z parameter, Y parameter, H parameter, and ABCD parameter not used at a high frequency? Now, if you consider that a Z parameter, then that equation is about what I supposed to be considered a two-port network now. Okay, so in this case, it is about a V1, V2, and we have this Z11. Okay, so we can say that a Z12, Z21, and a Z22. And here we have I1 and a I2. Now, if we take an example of a Z parameter, to obtain this Z11, we need to consider that a V1 and a I1 here. So means we have the ratio of a V1 by I1. In that case, that I2 is equal to 0. Okay, if I2 is equal to 0, then we'll get the Z11 parameter. Now that current is equal to 0 in a given particular circuit, what do you mean by that particular factor I2 is equal to 0? Current is equal to 0 means whether it is a open circuit or a short circuit. Okay. Now, if you consider here, when we say that for a given particular circuit, then if it is a open, okay, this particular circuit, if it is a open, then a current particular at that particular port is equal to 0 now. And if it is supposed to be considered that a short circuit at that particular point, voltage will be a 0. Now, at that particular port, when we open circuit or a short circuit, using this open circuit and a short circuit, we can find out this Z parameter, Y parameter, or H parameter, or that ABCD parameter. Means we are using a current or a voltage that is to be used at a low frequency to model your linear circuit. But at high frequency, there is no current because it is wave is propagating. So at a high frequency, it is not able to realize the current and voltage at a high frequency. So then, and again one more thing, because we are not able to realize that current and voltage, again we are not able to go for the short circuit and open circuit at a higher frequency. Means it is very difficult for the short circuit and open circuit at a higher frequency. And then the issues of a short circuit and open circuit, and then issues of a measuring the voltage and current at a given particular port in a network at a high frequency, it is difficult. So that's why that another parameters have developed, so those will model your microwave circuit, and that parameters are called as a scattering parameter. So scattering parameters or S parameters are used to model your or to analyze a microwave circuit. So now in this scattering parameter, we can say that scattering. The word is about a scattering parameter. Now scattering parameters means what? At a given particular port, that when we apply a signal or a wave, so that signal will be scattered from the given particular port. So based on that input and output characteristics of a port, we will define or we can analyze the microwave circuit. So that's why we say that a S parameters are highly useful to characterize a linear network at a microwave frequency or at a high frequency. Okay, means high frequency, that is nothing but a microwave frequency. And then the way to define this or to characterize a linear circuit is just like we need to consider that a incident wave, okay, and then we need to use a that particular port, that is about a reflected wave. So at that particular port, wave is incident or wave is to be transmitted through that port, and then at the same time it is to be reflected. So we need to use the two parameters. One is about the incident and one is about the reflected wave. So we use this incident and a reflected component to define the scattering parameter. Again, one more term at the same time, when we are going to consider the incident and reflected wave, we need to consider the match determination. Match determination means what? Termination means what? A load. Okay. So we can say that a match termination or a matched load means port is to be matched. So at that particular wave is incident at that particular port, the same time there will be a reflection at that particular port. Okay, so that's why we need to use a scattering parameter or S parameter, and that will represent the or that will use to analyze the microwave circuit. Then again, one more way, instead of measuring that S parameters through that incident and the reflected waves, or another way directly we can measure a S parameters through the vector network analyzer. So that can be used to provide you the directly those S parameters there. So now a given network, suppose we consider that a network is of a two port now. For the given particular two port network, what will be the parameter? But that S parameters can be applied for the nth port of a linear microwave circuit. Here we'll take example here for the nth port network. Now suppose to be we consider that this one is about a port 1. Okay, so we can say that a port 1 here, then we have the another port here, that we say a port 2 now. Okay, this one is about a port 2 here. Then we say that is about a port 3. Likewise, we can consider that, okay, then we say that that is about the port n. Okay, so now we say that 1, then port 2, port 3, and a port n. So then we supposed to be consider that there are the n type of a ports here. Okay, so we can say that a port 1, port 2, port 3, and a port n, these are supposed to be n type of a port here. So now for each and every port, there is some incident wave and there is some reflected wave. So we supposed to be consider here, there are the defining the a S parameter. We need to consider that wave incident at the given particular port. This is supposed to be considered that This one is about a incident wave in a given particular port there. Okay, so that we can say that is about a now. And for the given particular port, so that's why a port 1, so it is about a A1 now. And a reflected port at this particular port here. Okay, so that is about a port B here. So we can say that a B here. So means here it is about the internal one for the port 1, and this is about a port. That is about incident 1, and this one is about a reflected. So similarly for a given particular port, we supposed to consider that there will be a incident wave, that is the A2 here, and then we supposed to be consider that there will be reflected wave at the port, that is called as a, we say it is about a B2 now. Or we can say that instead of a reflected, we supposed to say that for a given particular port, this one is about input at a port, and this is about output value. Okay, input value and output value. Okay, likewise, we supposed to. Similarly, we have the incident wave at a port 3, that we can say that A3 here, and we have the reflected wave at port 3, that we say that is about a B3. Then we say that here we have the Bn for the nth port, and here we have the An, that is for the nth port. Now, how to represent this S parameter or that S matrix there? So simply you know that a Z parameter and H parameter you can represent, okay, in terms of what we can say that voltage and current. So here we can say that S parameters are represented in terms of what, a incident wave and a reflected. So simply I can write here that S parameters are representing here, how they are representing there for the given particular port. We supposed to say that we have the port B is the output here. So we can say that we have the S here, that is about a scattering parameter or S matrix, and we supposed to say that we have the that about the incident wave. So this way we can define your S matrix. So B is nothing but what, a output at that particular port, means that is about a scattered one. It's when we can say that wave is incident at a given particular port, then that wave will be scattered from that particular port. That is about a scattering one. So that's why it is called as scattered parameter. The scattered waves at a various port, okay, whatever we can say that at a given particular port, suppose that is about n port, that scattered wave at that particular port is dependent on the incident wave. Suppose I am saying that a port 1 here, so incident is A1 now. Okay, incident is about A1 now. Then the scattered I say here, okay, so we can supposed to be consider that this one is about a scattered one. Okay, so likewise, I suppose to consider, sorry, B1. Now that is about is scattered here. This one is about A is about incident 1. Okay, A is about incident 1. But that B1 is about a reflective, scattered from that given port. So that scattered waves at that particular port, at any port in a network, in a microcircuit, so that depends upon the incident wave. Okay, that depends upon the incident wave at various ports. So we can define the expression of that scattering parameter, that is about a B1 at a port 1 here, and that B1 is dependent on the various ports, because it is scattered one, scattering from the network. So that B1 at a port 1 is dependent on the various inputs of the that port here. Okay, means various incident waves at a various ports. So I'll write here the expressions for the scattering parameter here. I'll say that for the S mat parameter, we can say that a B1 at a port 1 is equal to, okay, B1 at a port 1 is equal to S11, that is about the same port 1, with respect to A1 plus S12, okay, with that is about A2 here, then S13, A3. Similarly, we can say that S1 R is supposed to be considered that is about the R port here. Okay, so in that particular diagram, and then we're supposed to be consider that we say that S1 AN. Okay, like so that is about 1 to N. So even we can no need to write this again. So even we can say that S1 N. Okay, no issue. Similarly, scattered wave at a port B, sorry, port 2, that is about B2 is equal to S21 A1 plus can say that S22 A2, S23 A3. Then we can say that S2R AR plus S2N AN. Okay, S2N AN. So likewise, we can write the expressions for the nth port now. So suppose I am saying that a nth port, a Bn here. Bn is equal to what? We supposed to say that Sn1 A1 plus Sn2 A2 plus Sn3 A3 plus. Again, we say that there is a nth R now, AR, or we can say that plus Sn. Okay, so we can say that N. This one is about your scattering matrix. But if you put that scattering these equations, all these expressions here, we can write in terms of matrix there. So we have a B1, then we can say that is B2. So likewise, we have a B3, B4. Okay, so we can say that B3, B4. Likewise, we're supposed to say that about a Bn is equal to, we say that S11, S12, S1n. Similarly, we can say that S21, S22, S2n. Then we can say that Sn1, Sn2. Okay, we have the likewise others. So we're supposed to write here that S and N here. And that is about the incident wave component. That is called as the A1, A2. Then we say that is about the AN. So if I write here this particular matrix, so I supposed to say that we have the scattered component or reflected component at a various port there. And we say that a scattered parameter that is about a S here. And we say that a incident parameter at this various. So that is about a P is equal to S into A. So this particular S, that is nothing but what? A scattering matrix or a scattering parameter or a S parameter or a S matrix. Okay, so S matrix. Okay, so this one is nothing but a matrix. So you can say that a S matrix or a scattering matrix, or you can say that this parameter is called as a S parameter. So from this, we need to define a properties for the S parameter. So this one is about the network representation in terms of a scattering matrix. So in that case, we say that reflected wave, they are the scattering parameter, and these are nothing but what we can say that is about the incident wave. This one is about it. This way we can represent the network. Suppose I consider here, okay, suppose I am going to consider here, I have a two-port network. Okay, so now we supposed to be consider that this one is about a two-port network. So in that particular case, so we have the B1, a B2 here. In that case, we say that S11, S12, S21, S22 here. Then we say that we have a A1 and a. Okay, so now this one. These are about. So if I write in terms of a expression here, so we'll say that S11 A1 plus, we can say that because we supposed to say that this particular way we need to write multiplying this particular factor here. So what we can say that this one is about a S1 to A2. So then we supposed to say that in terms of a B2 here. So we write here S21 A1 plus S22 A2. B2 is equal to what? S21 A1 plus S22 A2. Now, in terms of a network, okay, a network diagram, or you can say that a microcircuit, how your ports are representing here. So this one is about your port one. We supposed to be considered this one is about your port one here, and this one is about your port two. So for a port one, so here we have the S11. Here we are getting the S12. Here we are getting the S21. Here we are getting the. Now we again redraw diagram here for the given network. So here we can say that there is some impedance that we supposed to be say that Z the impedance, and we are applying some voltage here that is supposed to be a VG for the given particular port. And then for these, we supposed to be consider one load here. Okay, some impedance. So I supposed to be considered about a load now. Okay, that is about a impedance. So now for this particular diagram, we consider that there will be an incident wave. There will be an incident wave that is called as the A1 here, and there will be a reflected wave at this particular port. There will be a reflected wave, and this reflected wave at this particular port will be a B1. So similarly, at this particular port, reflected wave that will be a B2, and here we say that the incident wave at this particular port will be a A2. Now this one is about the representation here. We can say that a S parameter representation. Now from this, we can talk about that what are the various properties of the S matrix. Okay, I just consider the two port network. Similarly, if it is a three port network, then B3 will be there, another row will come, then A3 will come. If it is a B4, another fourth port is there, B4 will come. Okay, then there will be two row and there will be A3 and A4. So this one, we can say that B1, B2, B3, B4 likewise, A1, A2, A3. So similarly, we have the rows for this S matrix there. So we will see here first what are the various properties of a S matrix. So we can talk about that. Properties of S parameter or a S matrix. Okay, so that is about a scattering matrix. So why scattered? Because at that particular port, your wave is scattered, means it's reflected from that port. So that's why we can say that is about a cathode. We incident a wave at that particular port, and then it will be immediately it will be scattered from that given particular port there. Means it is out from the given particular port. That is called as a scattered one. So that's why we say that it is about a scattering, or you can say that a scattering matrix there, or scattering parameter. Then what are the various properties there? So S matrix, okay, that we can say that, or we need to talk about that always, that S matrix now. That S matrix, it is always a square matrix. It is always a square matrix. Okay, yes, matrix is always a square matrix. That is about it. So if you consider that, a S matrix here, if we have the N port of a network, for the N port of a network, that S matrix is about the N into N. Okay, for N port network, the matrix S matrix will be of a N into N port. That's why we can say that S matrix is of a square one. It is always a square matrix. Okay, yeah, that we have said that how many number of ports we have according to that number of incident and number of reflected component at that particular port always same here. Then another is about, we can say that S parameter, or we can say that elements of that particular S parameter, we say here elements of the S matrix are represented by the ratios of the complex feature. Complex feature means what? We can say that A can be a complex one. Okay, we can say that whatever the, we say that a given particular port, that is about A here. So A can be a complex quantity. Okay, that we can say that A will be a complex phasor quantity. Okay, so you can say that we have this particular, it has a magnitude something I supposed to be right here in terms of I x plus j y, like that. It has some particular component. So it has a magnitude as well as it has a phase. So it can be a complex, that elements of the S matrix can be a complex, and that element represent the ratios of that particular complex page. Okay, that elements of the S matrix, they have the ratios of this complex page. Then we can represent the S matrix here in terms of a ratio. We say that S is equal to what? I and a J. And that I and J, we say that this one, we say that we have the BI is nothing but the output here, and AJ is nothing but the input here. So when this will be true, when we can say that all ports are matched except, okay, all ports matched, terminated, except, what is the exception here? Except that port J not matched. Okay, except for port J. All other ports are matched, terminated. Means matter means what? Termination is a match. But only that port J is not matching. So in general, we will get that Sij, that will be a complex one. If these are the complex quantities, so we will get the S matrix will be a complex one. So all the ports to be matched. So now, if you see here that notation of a I and J, so I term that define a output here. I term define the output, and J term define the input. So first term is defining the output, and second term, okay, that's subscript I and J. If you see here, the first term is defining the output, and another term defining the input here. Okay, so you just remember always that Sij here. Okay, that's about what we can say that for the given particular S matrix or defining the S parameters. In that case, a first element, first subscript to be defined, that is about a I term and a J term. Okay, I term is nothing but output, and J term is nothing but a input here. And then from this we say that even if we say that BI and AJ, so that some particular ports are there in given a line, if we consider any circuit and that is connected to a line here, so in that case, that produces that impedances at this particular port will be a unequal. Okay. So for this S matrix, so if we say that a junction or that particular port is perfectly matched, okay, I supposed to be right here. If that port, when a port I is perfectly matched, if port I is perfectly matched to the junction, what do you mean by the junction? Junction means what? We have the a microwave component. They form a junction there. Okay, whatever the component. So when I port is perfectly matched to the given junction or that particular input port at that particular junction, it is perfectly matched. Then II, SII will be equal to 0. Okay, SII will be equal to 0. Then another case is what? Condition is that when we have the ports, when a port I and a J, okay, port I and J, both ports are perfectly isolated. Perfectly isolated. If that port I and J both are perfectly isolated, so in that case, we say that Sij. Here we can say that I is nothing but the output and J is nothing but the input. Now, even if we are providing the input to the given port, so then that Sij or Sji, that will be equal to 0. Okay, that will be equal to 0. Then next one, the diagonal element of a S matrix. If we can say that whatever the diagonal elements there, diagonal elements of that S matrix, they represent the reflection coefficient. You can say that the diagonal elements are nothing but to be represented as a reflection coefficient. Now, what are those diagonal elements? So earlier we have seen that a two-port network, we say that S11, S22, these are nothing but the diagonal component. Okay, so means for a given particular port, so reflection coefficient at a port I, suppose we have the port I, we're supposed to say that we have a port I for the given particular port I. So then the reflection coefficient is nothing but what? SII. Okay, that reflection coefficient will be SI. But the condition is that there will be a mass termination at all other ports. Okay, so whenever we obtain this S matrix, we need to terminate other ports with a match termination. So if you see that a low frequency component Z, Y, and ABCD or H parameter, in that case we are using a short circuit or a open circuit. But in the case of S matrix, we need to consider to obtain the S parameter at any port, we need to use that concept of a match termination. So all other ports to be a match terminated. So in this case, a diagonal element, we say here, that diagonal elements are nothing but a reflection coefficient. For a given particular port I, suppose I am saying port I, that SII, that will be the a reflection coefficient at a port I. SII will be the reflection coefficient at a port I. I is the input and reflected again I. So that's why I, that is about a reflection coefficient. So in that case, suppose I is equal to 1. So I say that S11, okay, that is nothing but a reflection coefficient. If I supposed to be a 2 here, then S22, that will be the reflection. So similarly, whatever the diagonal elements I say here, S11, S12, suppose I am saying going to like write for the three port S matrix there, S21, S22, S23 here, S31, S32, and S33 here. So in this case, What are the what are those diagonal elements? These are the S11, S22, S33. These are nothing but the diagonal. So these diagonal elements to be considered as a reflection coefficient. If that particular port is a match, okay, that if that particular port is a match, then there is no reflection. Okay, so that's why we can say that at that particular condition, okay, so then this component will be a zero. Okay, so we'll see, okay, that particular reflection coefficient when it will be a zero and all. So you just remember that a given particular port, okay, so that port is nothing but what we can say that a diagonal coefficient of that particular port are nothing but a reflection coefficient. So then another is about what we can say that if for a reciprocal network, okay, that S matrix or S parameter, supposed to be right, S matrix or S parameter is symmetric one. Okay, S matrix is a asymmetric one. So what do you mean by asymmetric? Symmetric means what? Sij is equal to Sji. At what condition? Condition is that I is not equal to j. I is not equal to j. Sij is equal to Sji. For I is not equal to a j here. So that is about a condition. So what we are saying earlier, if you see that we have obtained the S matrix representation in the nth port there, and we supposed to be consider that there is one reference port that is about a R port we have seen. Okay, so for this reference port, so when we obtain the S parameter with respect to the R port here, so in that case, what we can say that SII is equal to what? SGI, that is about a symmetric one. Or we can say that SIR, because it is, we consider that with respect to that a reference port. So that SIR is equal to SGR. Okay. So that is about what you can say that this I and J ports, that ports are electrically symmetrical one. That ports are electrically symmetrical. Which port? Okay. Now which port are that I port and port J. Okay, port I and a port J. Both are electrical symmetrical with respect to what? With respect to that R port. If they are electrically symmetrical with respect to port R, we say that SII is equal to SJJ, and we're supposed to say that SIR is equal to SGR if it is a electrical symmetry. If that port I, okay, another condition. If this port I and port J, this port I and port J are electrically anti-symmetrical. Okay, so I supposed to be right here. Okay, anti-symmetrical. Okay, if the port I and port J are anti-symmetrical with respect to port R, so in that case, what? SII is equal to SJJ. That is true because it is, we say, symmetry property. But we say that anti-symmetrical with respect to port R. So in that case, SIR is equal to minus SJR. Okay, SIR is equal to minus SJR. Because we say here that is about the ports are asymmetrical, electrical symmetrical port I and port J with respect to R. So that's why this ISIR is equal to SJR. If it is anti-symmetrical there, then the SIR is equal to minus SJR. Next one, then all these S parameters defined, or it is to be used for the passive network. Okay, that is for the passive network. So means that passive network, that that network we supposed to be considered is a lossless network. So in that case, for a lossless network, for lossless passive network, for a lossless passive network, so in that case, the S matrix is a unitary, is unitary. Now we say that a S matrix is unitary. So from this, what we can say that unitary property means what? If we have the S matrix there, and if we are taking a transpose of this S matrix and a complex conjugate of this S matrix there, then it will be equal to what we can say that a identical matrix, that is about I. So from this unitary matrix, that unitary matrix has the two important. One is about a zero property, and another is about what we can say that a unitary property. Sorry, unity property, not unity. It is about a unitary one. Okay, so unity property. Now, what do you mean by this zero property? In a zero property, we supposed to be consider that the sum of the products of each term of any row multiplied by the complex conjugate of the corresponding terms of any other row. Okay, so that is summation will be a zero here. Means we can say that summation of S Pj into S Qj, okay, is equal to 0. Okay, so that is about a zero property. The summation of, here we can say that j is equal to 1 to n, or we supposed to be consider that I is equal to 1 to n S of Ip into complex conjugate of a S of Iq. Okay, here we can consider that a sum of the products of each term in a row multiplied by the complex conjugate of the corresponding terms of any other row. Okay, corresponding terms of any other row. In that case, it will be 0. But here in this case here, SIP is equal to SIQ here. Here it is about the sum of the products of each term of any column. Okay, here we can say that a column, any column multiplied by the complex conjugate of a corresponding terms of any other column is equal to 0. That is called as a zero property. Here is about a row, there is about a column. Then next is about a unity property. So in the case of a unity property, earlier we say that a sum of the products of each term of any row multiplied by complex conjugate of any other row. Now here, the sum of the products of each term of any one row. Okay, so I suppose again I'll just write here. Okay, so that is about unity property. S I j is equal to S I j complex conjugate is equal to summation of j is equal to 1 and bracket of Sij bracket square is equal to 1. So here the sum of the products of each term of any one row multiplied by, okay, any one row multiplied by a complex conjugate of, okay, here this is, we can say that complex conjugate there multiplying here this term, so we'll get that is equal to 1. That is about a unity. So we can say that Sij with respect to the complex conjugate of this, we'll get that a 1. So similarly, we can say that sum of the products of each term of any one column. So instead of that, we talk about that a column also, Sij here into a Sij complex conjugate there, or we can say that Sij bracket square I is equal to 1 to n is equal to 1. So here the sum of the products of each term, here column, and this one is about a row. Each term of any column multiplied by its complex conjugate is a unity here. So that is about a zero property and a unity property of this particular, uh, okay, okay, this yes matrix here. That is about, that's all about a matrix parameter. And one more parameter, that is about a shifting of the reference plane. Shifting of the reference plane. So how they are shifting of the reference plane? We can say that we write the S matrix here. So we supposed to be consider that a diagonal here of, consider now, e raised to plus minus j beta ln here into S here diagonal e raised to plus minus j beta ln. So this is about the location of the reference plane for this given particular phase here. Okay, that will be shifting here. The shifting of the plane, that does not change the values in terms of magnitude, but it change the phase of the given particular parameter. So these are about the relation between that reference plane shift and the parameter phase shift, and that can be expressed in terms of a e raised to minus j beta ln diagonal of e raised to plus minus j beta ln.